Okay.
Now, the first order of business is, well, for one, these spotlights are very hot, so I want to make sure whether or not I need them. So, just write some things down. In all my colors. For like 5 seconds, and you guys are going to go home and watch the video and tell me if you can still see everything clearly, because if you can, I'm never using these again. And then, okay, but for today I shall suffer for the art, and we'll move on. So, today's quiz actually does count. The quiz last week was a diagnostic, as I told you guys. And for those of you who are new, sorry that to start it off like this, but we'll have a quiz every week. So the beginning of every week, the class will start with a quiz. And the quiz in general will cover things that we spoke about the week before. But the first 2 quizzes were algebra and trig, basically. Things that you were expected to know before being in this class. So how we're going to start off today, and actually a part of tomorrow probably, is we're not going to start calculus right away. I actually do want to review a couple topics with you, and that is I'm going to do a crash review of exponentials and logarithms. Because as the class goes on, I'm going to derive a lot of things for you, and the easiest way to derive a lot of these things is to use exponential and logarithmic functions. And people tend not to be as familiar with those as they should be. Same can be said of trig functions, same can be said of a lot of things, but these in particular, because people tend to only have seen them once in their life, as opposed to all the other things. And so I just want to make sure you understand these 2 kinds of functions very well, because we will be using them, and we'll be using them theoretically as well as just doing computations with them all the time. So let's actually do that, and this will probably spill into a little bit of tomorrow, and then we'll officially start calculus tomorrow towards the end of the class, I guess. Okay. And of course, you should note that I did say tomorrow, even though it's Thursday. That was not me misspeaking. Tomorrow is actually a Monday schedule, according to City College, according to Q. Okay. So you guys should be here early tomorrow, because we'll continue. Okay, so let's actually jump into it. Let's start with exponentials. So, and I just do want to emphasize that this is a crash review, so it's not meant to be completely exhaustive or comprehensive, and I'm not going to give you a lot of examples. I'm just going to kind of want to remind you of some facts that you should know relatively quickly, and because we're going to be using them all the time. So the form of these guys, it's something like x to the a or something similar to that, where the a is called the exponent or the power, and the x would be called the base. And when a is a positive integer, it represents repeated multiplication, right? So if I have x to the 5th, it just means x multiplied by itself 5 times. And by generalizing that idea, we can come up with a lot of rules, which we call the laws of exponents. So start with 1. If I have something that looks like this, and I multiply something that looks like that, what is the result? You add the powers. Multiply things with the same base, you add the powers, right? And this is because this is x multiplied by itself a times, this is x multiplied by itself b times. In total, you'll have a plus b, x is multiplying. 2, if you have something like this divided by something like that, what is that? You take the top power and subtract the bottom power, right? And if you can write this out and write that out as a multiplications, b multiplications, the cancellation law will tell you that that will actually work out that way. Of course, here we're assuming that x is not 0 because remember, lecture 1, we can't divide by 0. And 3. Let's say I have an exponent and I raise it, an exponential quantity, and I raise it to another exponent. What happens here? You multiply the powers. 4. What is x raised to the 1? It's just x, right? Based on the definition, this is just multiplying x by itself one time. 5. What is x to the 0? That's 1, assuming that x is not 0 itself. The way you would figure that out is if you plug in a and b are the same in this equation, you will get x to the a over x to the a, which is 1. And here you have a minus a, which is 0, so you get x to the 0 is 1. And x cannot be 0 here because we have division. Okay, so that is another rule. Now remember I told you powers did not distribute across sums, but they do distribute across multiplication. So there's a rule that tells us that if we have two things being multiplied and I raise the product to a power, that power does distribute across the multiplication. This does not work when there's an addition or a negative sign in between these, for the really youngest. 7, this also works with division, because division is kind of just a weird kind of multiplication. So powers will distribute across division as well. 8. 5x to the negative a, what does that mean? 1 over x to the a. And again, because there's division here, x cannot be 0. So that's another one. And again, you can use this rule to prove that. If you plug in a equals 0 and b equals a, you would immediately get this as a result. And of course, we can't divide by 0, so that's not a thing. Here's one that students often forget or just kind of mix up. If I have x to the a divided by b, what is that? Yeah.
X to the a power, but this is the square root of b. Not root of b, not that, not square root.
The b's root.
Yeah, b root.
Right. Or you can do the bth root of x and then raise it to the a. These are always the same as long as your x is greater than or equal to 0. Of course, if your x is less than 0, one of these might make sense, whereas the other doesn't. So for example, if b is an even number, then this is not going to work, right? So, but as long as they're both 0 or bigger, these two are always the same, and one might be easier to work out than the other one. So for example, look at example here. If I have 9 to the 3 halves, there are two ways I can think about that. One way is to think about this as the square root of 9 cubed, but since because 9 is greater than 0, I can also think of this as the square root of 9 cubed, right? Now this one is harder to calculate, right, because you have to cube 9, it's going to be a big number. But this one is easier to calculate because the square root of 9 is 3, and then you cube that, so you get 27. So sometimes the way you think about it can actually make your life easier A lot of times, taking the radical first and then raising it to the power is going to be easier computational. And in this class, you're not allowed to use calculators, so you do want to know, in general, a quicker way to compute things. A very common one here that you can know from this rule is that x to the half equals the square root of x. A lot of students just know that by heart, but this is the rule that's being applied when we have this here. Now, for those of you who did not remember that, there's a nice little mnemonic which even I use these days, still, called flower power. And so, if you have x to the a over b, what I do is I think of the a over b as a flower, where the bottom is the root and the top is the flower, which of course rhymes with power, hence the name flower power. So I know that if I have x to the a over b, the bottom number is the root, it's going to be the radical, and the top number is going to be the power, which rhymes with flower. Just throwing that out there. In case you're one of those people who you can never remember who goes where again. But you can also remember that via a law of exponents, because you can think of that as x to the a to the 1 over b by, I don't remember which rule number 5 or 4 or 5 or whatever I wrote. And so that you will remember, okay, the a is in the power because I can do that multiplication. So those are just the basic generic laws of exponents, and they all kind of stem from one assumption on what it means to raise something to a power. So there's that. Now let's talk about an exponential function. The quintessential one is something that looks like y equals a to the x. Okay. Now here, normally, a is considered to be greater than 1, or at least it's considered to be positive. Often, we'll consider a greater than 1, and that will come. So these are some assumptions here. And I'll talk about this a little bit later, in a few minutes in fact, that if you know how it works for things greater than 1, you can know how it will work for things between 1 and 0 pretty easily by using the rule number 8 that I put down there, where x to the minus a is 1 over x to the a. Okay. So this is called an exponential function. I want you to notice that here, the base is a constant. It's going to be a number. And the power is a variable. This is very different from a polynomial, where the base is the variable and the power is a constant. Right? Or any such, like a radical function or things of that sort. Right? So there's this kind of function. It's a very important kind of function. I want you to remember what the graph of such a function would look like. So that's an exponential function. I want you to also note these functions obey the above laws. So, for example, if I have f of x equals, say, a to the x, and I have g of x equals b to the x, then if I think of what the multiplication function would look like, well, it's going to be a times b all to the x, right? You can actually apply the laws of exponents on the function level. So that's the first thing I want you to know. Laws of exponents will work with the functions also. Another thing I want you to know is what the graphs of these look like. In particular, I want you to know what the graphs look like for a greater than 1. So if I have y equals a to the x, we're assuming that a is greater than 1. What does the picture actually look like? Right, looks like that thing. It's like that. And so here, you'll notice that as x gets very small, as x approaches negative infinity, your y will approach 0. And as x approaches positive infinity, your y will approach positive infinity. So it goes like this. Here, it will pass through the number 1, y, because when you plug in 0, you get a to the 0, which is 1. We have that as a rule. And so that's what that graph will actually look like. We're going to have nicer language to express this kind of idea pretty soon after we talk about infinite limits. But for now, that's kind of an idea you should know. We say the x-axis is an asymptote of the graph. It's a horizontal asymptote. I also want you to recall we can transform these. So, for example, you should know what y equals a to the minus x would look like. What would y equals minus a to the x look like? What would y equals minus a to the minus x look like? These will all have pictures that you don't have to plot points. By the way, on the first quiz, when I was looking over some of them, I'll give those back to you tomorrow. On the last page where I had you guys drawing a bunch of graphs, I saw some people were literally like plotting points to draw the graph. They plot like 6 points to draw a graph. You're too old for that. None of that anymore, right? There are certain basic graphs that you should just know how to graph by heart. You shouldn't be spending time plotting points. In general, plotting points is a very inefficient way to draw a graph very quickly. Of course, they're going to be, curve sketching is a topic that we're going to cover in detail in this class. There are going to be a few points that you should be plotting, like the x-intercept and the y-intercept. But if you're like plotting 10 points to figure out what something looks like, you're being very inefficient, and it's just something that I consider beneath a Calc 1 student at this point. You should just know what something looks like. But you shouldn't have to plot points to figure out what does y equals x squared look like. You should know what y equals x squared look like. What would this one look like? What happens when I make x negative? Reflection where?
Across the x-axis.
So across here? No, across the y-axis, right? So that graph is going to look like that. This one, when I make the outer value negative, that reflects in the x-axis. So that will look like that. And then this one is just reflecting that, so that one would look like this. Right? So you knowing what a graph looks like, I can manipulate that graph arithmetically, and you should know how the picture is going to respond to such things without having to plot points to figure it out. You should just know that that's how things would operate. Versus, if I add a number to this, you should know it would shift up. If I subtract a number from that, you would know it would shift down, etc. I expect you to remember all of that stuff. Now, one thing, another idea that we will explore later on, but I might as well just mention it now since we're already here. Exponentials grow faster than polynomials eventually. That is to say, and again, like I said, I'll extend this relationship further and we'll explore it a little further when we talk about limits. That is to say, if we're looking at a to the x, where my a is greater than 1, this is going to be much bigger than something that looks like x to the n, where n is a positive constant. As x gets large. Okay. So this is just a symbol that means way bigger. So So a lot of times you'll be sketching something on a piece of paper and it will escape you the significance of how these things relate to each other based on your sketch. I mean, if you were to sketch like y equals x squared, which you should know looks like that without having to plot any points, and you were to, so this is y equals x squared, and you were to graph, say, y equals 2 to the x, what's on that, y equals 2 to the x. Now, when you graph them on this scale, they seem to be not much difference. Yeah, the shape is different, but they're not very much different other than that. And you would be wrong, right? So here, this is a case of expectations versus reality. So here's the expectation here. Not much different based on this sketch. But the difference starts to shine when your input gets larger. So if I were to draw that same picture on a much larger scale, so let's say here and here is like you have a huge x input, right? So x is going off to infinity. A billion, gajillion, majillion, virgillion, whatever, right? And of course your 2 to the x is going to look like this. So let's say we zoom out, right, really big, really far. What do you think the x squared is going to look like on that kind of scale? It will be indistinguishable from 0. An exponential will eventually grow so much faster than any other polynomial that the polynomial might as well not even be trying. Okay? And it does not matter which exponential and which polynomial you pick. I can pick 2 to the x and x raised to the 1 billionth power. Eventually, that's going to happen. 2 to the x would be so much bigger than x to the 1 million that x to the 1 million might as well be nothing. Okay? So exponential functions have this very special property. They grow a lot faster than polynomials. They will outmatch any other polynomial on a large enough scale. That's going to be an important thing to remember. So that kind of tells you, yeah, you sketching the graph might not give you that impression when you're drawing at a small scale, but you should know that these are two very different kinds of functions. They do not behave the same whatsoever. Now, so that's the reality of the situation. And when we're doing calculus, this sort of reality is going to become relevant quite often. So, I'm not sure if that's something that you would have talked about in pre-calc, but that's something I expect you to know at this point. So we looked at the laws of exponents, we looked at the graph, and now we kind of see one of the major differences between exponents and polynomials, which is something that we've often looked at prior to this class. Now let's talk about a particularly important exponential function. There is an exponential function that stands above the rest, that holds a special place in our hearts. It will hold a special place in our hearts from now until the end of your mathematical journey. Does anyone know what I'm going to say? Huh?
Is it e to the x?
E to the x. You might say, that's not an exponential function. The base is a variable. It is not a variable. E is a constant. Right? We just call it by a letter. But every time you see E in some sort of mathematical expression, it is usually referring to a number. Kind of like pi. When you see pi somewhere, you don't think of it as a variable. You automatically think of it as a constant. 3.14159, that thing that deals with circles. At least that's how you would have been introduced to it. It's a lot more important than that. But E is a similar kind of number. Right? So E to the x is an exponential function. Your E is roughly 2.71828 It's a non-repeating decimal, non-repeating infinite decimal. So no one has ever written down e in its entirety, no one ever will, similar to pi, which makes it an irrational number. Not that it's crazy or it's not rational, but that's a very specific name. That means it cannot be written as a fraction. We can approximate it with a fraction, but we can't actually write down exactly what e is as a fraction. Now, most of you probably won't ever get to this level, but for those of you who are going to be math majors, in a few years you're going to remember this. You're going to go, oh yeah, Jhevon told me about that. There is a textbook that math majors often go through when they're going into graduate studies. The best way to describe that textbook is infamous, right? It's Real and Complex Analysis by a guy named Walter Rudin. And when you're a math guy, you'll either love this book or hate this book. There's no in between. A lot of people swear by this like their Bible, and a lot of people are like, nah, I can't do that because, like, who could understand that? It's written so terse and short. Anyway, in the prologue of that book, the first sentence of that book introduces e to the x, and then it says, this is the most important function in all of mathematics. That is the first sentence of that book. This function is not only an important exponential function, it's an important function in general. And at the end of this class, you won't appreciate just how important it is, but you'll start to know a lot about its properties so far. Where did this number come from, and why do we call it e? Well, so where did it come from? Well, it ultimately came from a thought experiment. So you pretend you deposit $1 into an account. And let's assume this account is compounded continuously. With interest. So this grows with compound interest. Compounded continuously means we're adding interest an infinite number of times. And then we're adding interest on top of that interest an infinite number of times at 100% interest rate. Now those of you who have done business mathematics and you're familiar with compound interest, you'll know that that grows like this. Where P is your principal, R is the interest rate, N is the number of times it's being compounded per year. If you look at this, pretend P is 1 and let your N approach infinity, just let it get bigger and bigger and bigger. That's what it means to be compounding interest continuously. Now you might notice that if this is a function of t, it's an exponential function. So it's going to start growing like that, right? And so now the question is, at the end of 1 year, so let's say you run this thought experiment for 1 year, how much money will you have? Right? So at first the answer is quite surprising because compound interest is an exponential function, which we know grow crazy fast. And if we're adding interest an infinite number of times at 100% interest rate, the initial expectation might be, oh, you're going to have an infinite amount of dollars in this account. The answer is, that's not true. You would have E dollars in that account. At the end of 1 year, you'll have roughly $2.72 under this crazy scenario, which is worse than any credit card that you will ever even theoretically own. The guy that figured that out was a guy named by the name of Euler. He's a Swiss mathematician. Named Euler. Figured this out. It's pronounced Euler. A lot of students read that as Euler. It's Euler because it's Swiss. And the E comes from his first name. So this is one of those guys like Newton or Einstein or one of the giants of old. He was a very prolific mathematician. There is so much math that we have today because of this guy. And he's rare in the sense of he's one of the mathematicians from antiquity that kept being prolific into his old age, which is pretty rare for anyone living more than 100 or 200 or 300 years ago. In today's day and age, it's very hard to be a guy like this because we have too much knowledge. No one knows it all. But back when this guy was walking around, it was possible for someone to walk around knowing about all of math in existence. That's no longer true. And so it's really hard to make contributions that really shape the entire field. But this guy made a lot of contributions that shape the entire field. Punched out a lot of theorems to the point where if you say to someone, oh, just use that theorem that Euler came up with, the response would be, which one? Right? He came up with tens and hundreds of really interesting things, not the least of which was this discovery. He thought about this and discovered that it doesn't go up to infinity. It actually approaches this number. It approaches it. And oddly enough, once you make this into an exponential function by putting x into the power, that function is super important to calculus and it is super important to mathematics in general. And we will talk about that function a lot. Moving on, let's talk about logarithms. We'll often abbreviate this logs. So for exponential functions, I expect you to remember all the rules of exponents, what the graphs would look like, how they compare to polynomials, what the important exponential function is, that is e to the x. Oh, by the way, I forgot to mention the name. E to the x is called the natural log, the natural exponential. So if someone refers to the natural exponential, they're talking about this guy because it's very natural to think of math in terms of this function. And when you're thinking of exponentials, math people tend to be thinking in terms of this exponential. And if they're given another kind of exponential, they're going to convert it to that kind of exponential to do the math. Because it's very important to be able to work with e a lot, all the time. Moving on to logarithms. Now, a lot of students are familiar with exponentials. If you're not familiar with this, in general, you'd be a lot familiar with exponentials. Not a lot of people are familiar with logarithms, but they're very important. Logarithms literally save lives. So this was invented by a guy named Napier to aid in nautical navigation because a lot of people back in the day would go out to sea and would never return because it was very hard to navigate large distances. So he invented a function that turned large distances into smaller distances so they can easier chart maps. And yeah, the invention of this function literally saves lives, but they're very useful otherwise. Here's a definition. The log of a number to a given base is the power that we must raise the base to. Get the number. Okay. That's what it is in English. Here's the notation for it. We write log to the base a of the number b. So b you can think of as being plugged inside the function. You can think of a log as like an f of x kind of thing, where you plug inside it. Sometimes we don't write the parentheses if there's just one thing beside the log, but that's the notation for a logarithm. The base is written way down here. So here is the base in that definition, and this is the number in that definition. Okay. Now what this definition says is the following. So we're going to look at laws of logs just like we looked at laws of exponents, and the first law is the definition. Right? To say the sentence in math language, here's what you would say. The log of a number to a given base is the power you must raise the base to get the number. What that means is, if I write an expression down like this, what it means is, if I take the base A raised to that power, I would get this number. So writing down this equation is exactly the same as writing down that equation. The difference is, here I've made the power the subject of the formula. A log is the power. It's when I want to think of an exponential function in a different way. Exponential functions are super important, but sometimes they can be very complicated to deal with, and so we've invented a function that kind of thinks about an exponential in a different way. And so an exponential equation can be written as a log equation and vice versa. You can switch between the two, and this is how you would do it. It's very important that you remember this. In fact, it's very important that you memorize all of these rules that I've been giving you today so far. You definitely want to be memorizing all of these, right? So that expression means that. So for example, if I write log to the base 2 of 8, what is that equal to? 3. Why? Because I have to take 2 raised to the third power in order to get 8. Okay? So you see log to the base 2 of 8, it's exactly the same as writing down the number 3. Okay? So you would say, why didn't you just write down the number 3 then? Why make this complicated? Well, here's why this idea is useful. And here's how it used to save lives back in the day. You see, logs allow us to downgrade the difficulty of a mathematical operation. This leads us to rule 2. It says the following. And again, here, think of our a as being larger than 1. And by the way, I forgot to mention this when we deal with exponentials. If your a is larger than 1, right? Then, let's say, then 1 over a is going to be less than 1, right? Easy to flip it. So, when we're looking at a to the x, and it looks like that, and we consider a to be greater than 1, and you might worry about, what if it's less than 1? Well, the less than 1 case is dealt with by this function, which by our laws of exponents is 1 over that one, right? So if you ever want to know about less than 1, just look at this function, right? So it's okay to pretend that we're bigger than 1. And once you figure out this case automatically follows, because all we do is just invert it. So we're always going to assume the base is greater than 1 in this class, unless otherwise stated. Between 0 and 1 is going to be very common as well, but we can deal with that case as well. Here's why logs is important. If I take the log of something raised to a power, like x to the n, what is the result of that? Yeah?
N log ax.
N log to the base ax. Logs will turn powers into multiples. So instead of raising something to the second power, you can now multiply it by 2 instead, which is going to be a lot easier. You'll get a lot smaller number in general, right? So if you take 3 squared, that's 9, but 2 times 3 is 6. The 6 is the smaller number. So you can take a very large number and turn it into a smaller number by using a logarithm, right? And that's how you can manipulate distances. And that's because a log is already a power. If you raise a power to another power, you multiply the powers, right? All that is in the background. Okay, so that's one rule of a logarithm. So if you have something like log to the base 2 of x to the 5, it's the same as 5 log to the base 2 of x. One thing I want you to note, which is very common here, if I write log to the base a of x to the n, it is not the same as log to the base a of x to the n. Okay? This is me taking a bunch of logs and multiplying them together. This is me taking the log of something where a bunch of them are multiplying together. According to PEMDAS, these are not the same thing, and it's very often where I'll see students think about this like that, and they'll move the power down here. It is incorrect to do it in this situation. You can only do it in that situation. You need to pay attention to your notations. So that's one way in which logs work. And I know I'm just kind of talking to you guys and giving you a lot of information. It's not going to be typical, but this technically from my point of view is review. I'm just telling you a bunch of stuff that you should know already, so you shouldn't be overwhelmed in general. If you are overwhelmed, it means you have a lot of review to do on your own. And in the text, in the syllabus, if you look at the topics page, I don't have a copy on me. Right, in the topics page, I actually gave you exercises for logs and exponentials, so just in case you don't remember them, you need to go and review them and do those exercises, right? So everything I'm saying today, I actually expect you to know already, but I want you to really fine-tune the details because they're very important and we're going to be using them in many different contexts. So that's one way a log can make things easier. They turn powers into multiples. Another thing a log can do is it can take a multiplication, and what does that become? Log to the base a of x plus log to the base a of y. Right? So they can turn multiplication into addition. Why? If you multiply things at the same base, you add the powers. And again, this, when you say it, it's log to the base a of x. Right? Language is important, so say it the proper way. Okay? 4. Logs will turn division into subtraction. Okay? Why? Because if I divide two things of the same base, I subtract the powers. We did that law earlier. So that's another thing that logs can do. Here's 5. This formula will have a name. It's called the change of base formula. And this basically says, if I have log to the base a of b, this is equal to log to the base c of b divided by log to the base c of a, where c is a conveniently chosen base. Now for us, e will often be the most convenient base to work with, and we'll see why. E, like I said, is a very important number, and e to the x it's a very important base to work with. So a lot of times if we don't have base e, we're going to want to transform it into base e by using this kind of equation. And just to show you an example where this might come in handy, look at this kind of expression. So, log to the base 4 of 8, what is that, right? So, by the definition, what it means is, I need to write what power I have to raise 4 to in order to get 8, right? So, you know, 4 to the 1 is 4, 4 to the 2 is 16. I'm already bigger than 8. So the answer is somewhere between 1 and 2. But where exactly? Is it directly halfway between, or is it something else? You're not sure, probably. And so you might think, well, I don't want to guess. How would I know for sure? The idea is 4 is not a convenient base when you're working with 8, right? What is 8 in base 4? Who knows that kind of thing, right? However, there is a convenient base for both of these we can work with. What do you think? 2. Base 2 would be very convenient. So if I can't think of what the answer here should be, what I can do is convert to base 2. So that is directly equal to this. Log to the base 2 of 8 is 3. Log to the base 2 of 4? 2. I have to raise 2 to the power of 3 to get 8, and I have to raise 2 to the power of 2 to get 4. So that's 1.5. So it turns out that 4 to the 3 over 2 is what's going to give me 8. I know that because this is the square root of 4 cubed by an earlier rule. Square root of 4 is 2 cubed, so that gives me 8. So whenever the base is inconvenient for us, we can actually change it. And we can change it using this formula. It's called a change of base formula. So here's an example where 2 is more convenient. For calculus, E is going to be most convenient. Must memorize the previous 5 rules that I gave you. There's no excuse. Okay? Next time I see you, those should be burned into your brain, which is tomorrow. So tonight, make sure you memorize those by heart. The following, you don't have to know them, but it's highly recommended that you just memorize them by heart. So I'm going to give you about 10 log rules, but the first 5 you definitely need to know. The second 5 you can actually figure out from the first 5, but why waste the time figuring it out if you can just know it? It's probably just going to be more convenient for you to know it. You'll be a better math student because of it. You'll be a less frustrated math student because of it, because you can do things quickly as opposed to slowly. And efficiency is important, not because it's always better, but it's easier to be a student if you're efficient. Right? You get less frustrated when you can get through a problem quickly, as opposed to it dragging on forever. So wherever you can be more efficient, you're going to want to take it. Here's the 6th rule that is kind of optional for you to know because it falls directly from a definition. What is log of 1? So log to the base a of 1, what is that? 0. Right? Now that you can figure out if you know the definition, because now you just have to remember, what do I raise a to what power gives me 1? 0. A to the 0 equals 1. That was a rule that we did earlier today. Right? So the log of 1 is always 0. Whenever you see log of 1, the answer is 0. It's always going to be 0. You just write 0. Think of it as 0. Don't write log of 1, write 0. Write the number 0. What's the log of 0?
But does it depend on what a is?
Hmm?
Do you have to know what a is?
No. So, and that's going to be something true in general. The rules are your templates, which means if I write a letter in some position, it means technically you don't need to know what that is. It'll work with anything.
So is it 0?
You think it's 0? It's not 0. How do we know it's not 0? Well, because if I take a raised to the power of 0, I don't get 0. What is it? Huh? Yeah? It's undefined. So if you see log of 0 at any point in your mathematical journey, 1, either you made a mistake, or 2, whatever answer you're looking for, there's no solution, right? Log of 0 is undefined. Why? If you have a positive number, there is no power you can raise it to in order to get 0, right? 2 to what power gives you 0? There's no power that will give you 0, right? If the base is 2, it will never be 0. Another thing you can know, which we'll talk about in a little bit as well, log to the base a of x is undefined for all x that is less than or equal to 0. In the same way, if I put a negative number here, that's never going to work. 2 to what power gives you a negative number? There is no such power, right? Because the powers don't affect the signs. If I make the power negative, it just flips the function. We did that rule earlier, right? So that's going to be true in general. So log of 0 is undefined, as well as log of any negative number is undefined. And again, that's something you can figure out by knowing the rule number 1 very well, but it's just nicer to just know that by heart. Let's look at an 8th rule. Here's one. If I have log to the base a, and I plug in a to the x into that, right? So you can imagine that there are parentheses. What is that? It's x, right? What power do I have to raise a to in order to get a to the x? Well, x. A to the x is a to the x, right? So if I put an exponential inside a logarithm, and they're at the same base, you can kind of think of the exponential and the log canceling each other and giving you the original input. That's easy to see from the definition. Here's another one that's less obvious. It's not hard to prove. You can prove it in 2 steps using the definition, but it's nicer to actually just know it. If you have a, and so you have an exponential function, but in the power, you plug in that kind of expression. Oh, sorry, I wanted this. Right? So I have an exponential with base a, and I plug into it a logarithm to the base a. What happens here? It turns out that you also get x. That's the answer. So if you plug a log into an exponential, and they have the same base, again, they kind of cancel each other, and you get the original input back. Now, there are some important things that these 2 rules give to us. So based on rules 8 and 9, if I look at the functions a to the x and log to the base a of x, what do these rules tell us about these functions? So knowing this, how can you compare these 2 functions? What would be a nice way to compare? Yeah? They're not equal. They're inverses of each other. Because that's how inverse functions behave. If I call this f of x and that g of x, then this guy will be g of f of x, and this guy will be f of g of x. So I'm saying g of f of x equals x, and f of g of x equals x. When does that happen? When when f and g are inverse functions, right? So inverse functions is another idea you learned in algebra and pre-calc. And so you should know, when you plug one function into another and they just cancel and give you the original input, it means they're inverse functions. Now that automatically gives you a lot of things for free. This kind of tells you, for example, what the graph of a logarithm would look like without you having to plot points, right? So here I have the exponential graph, y equals a to the x. Knowing that the log is an inverse, what would log to the base a of x look like? How do you find the graph of an inverse if you know the graph of the original? Yeah?
Reflect over y equals x.
You reflect in the line y equals x. So you're going to have here the line y equals x. Then you're going to take the mirror image. That will give you this graph here. So that's what y equals log to the base a of x actually looks like. Because this passes through 1, it's a mirror image, so this is going to pass through 1, which coincides with the rule we had, log of 1 is 0. We just saw that. Log of 0, you'll notice, is undefined. The graph will never touch that line because the exponential never touches this line. Also notice that this graph does not exist on the negative side because log of a negative is undefined. So this graph fits all the properties that we saw before, and we can get it easily because it's an inverse function of the exponential. Of course, with transformations, we get a lot of things for free with transformations. So log to the base a of x, you should know that that's what the graph looks like, passing through 1. If we were to write negative log to the a of x, well, that just means I flip this upside down. If I were to write log to the base a minus x, well, that's just flipping this and that. If I were to write negative log to the base a of negative x, well, that's just taking that and flipping it upside down, etc. Right? If I add a number to this, it's going to shift it up. If I subtract a number, it shifts it down. All that good stuff. So by knowing this, I automatically know what the graph looks like. I don't have to sit there like plotting 10 points. There's no what the picture is going to look like. And that also tells me a lot about the properties of the function. Log of 1 is 0. Log of 0 is undefined. Log of anything negative is undefined. Logs will grow slower than the exponential. The exponential is growing super fast. Logs will grow super slow. Logs, how they compare to polynomials is that the polynomials are bigger, right? So if I'm comparing log to the base 2 of x to x squared, the same way that the exponential beat the x squared is the same way the x squared is going to beat the exponential. If you go out far enough, the polynomial is going to be way huge, and the log might as well not even be trying. Right? So logs grow very slowly. They're one of the slowest growing functions we know of, and polynomials grow faster than logs, but not as fast as exponentials. Exponentials grow faster than the both of them. And here's the 10th rule, which is not really a rule, it's more of me telling you about a special notation that we will be using because it is quite traditional to use that notation. I told you E is a very convenient base. So to let this stick into the minds of students, we normally have a different notation for when we're specifically thinking of log to the base E. So when you're in calculus 1, 2, and 3, maybe even differential equations and vector calculus, this expression you will express in a particular way. Do we know what it is? Yeah? ln. Right? So we can do this. So when you see this expression, it is a logarithm. All this means is that the log has base e. Whenever I write this, it's just a logarithm. It follows all the rules, follows all the logarithms because it is a logarithm. So if you want to know how it behaves, what it looks like, you already know. It behaves and looks like that. Right? It is a logarithm like any other logarithm. We just give it a special name so that it kind of sticks out to you. And it is the logarithm that in calculus we will always want to use. And if I'm given any other logarithm, I'm going to want to convert that logarithm into an ln before doing any calculus. And we know how to do that by the change of base formula, rule 5. So that is, and this also has a name, it's called the natural log. Again, because it's very natural to work with this logarithm as opposed to any other logarithm. This one has a very special place in our hearts. Now, why e to the x and ln are so important, we'll kind of see a glimpse of that as we move on, but right now they're very important. I do want to make a note here. In advanced math, this means way beyond calculus when you start proving things and proving theorems and doing all that sort of stuff. And in places like Wolfram Alpha, which I told you about the first day of class. LOG means log to the base e. Right. So LOG is a generic phrase that means the standard logarithm. Now most people, when they see that, they think the base is what? 10, right? So for us, log x is log to the base 10. And the reason is, that's the most general one to use as the standard, because we have 10 figures. So engineers would use that because it goes 1, 2, 3, 4, right? So they use log to the base 10, and in a math class that's geared towards the general population, this will mean base 10, but it actually changes depending on the discipline. So if you're in a math class, and you're in a very high level math book, and you see that, base E is the standard. It means base E. If you're reading a very high level computer science textbook, the base would be 2, right? Because of binary, right? So that would be the standard. So the standard can change. For us and engineers and for the general population, this would mean base 10, but once you go far enough in math, no one uses base 10. Everyone uses the natural log, and so we make that the standard. So if you're typing in Wolfram to figure out the answer to a question, and you see this, you should know it means that, not base 10. Okay, so that I just want to mention that. Because if you check in a lot of computer systems, they're going to use this to mean ln, as opposed to how you not necessarily think of it. But in your textbook and in class, when I write this, I mean base 10. On Wolfram Alpha, it means base E. That's all the log rules you should know, and the notation. And we're pretty much done. So next class, I'm going to actually do some examples. So what I would say for you to do is maybe try these on your own, so that tomorrow we can get through them quickly, and then we can start calculus finally, right? So here are some examples to try. And simplify those. 2, expand as a sum of logs. 3, combine into 1 log. 4, and then solve these equations. copy these down and make sure you try them. And that will be just a general tip I will give you. Whenever I write down examples on the board and I say, try these for tomorrow, it behooves you to actually try them. Don't wait until tomorrow comes around and wait for me to write the answers on the board, even though I will do that. You will not get as much from the class if you're not working on it on your own time before just watching me do it. Right? You're going to be in that situation where I understand what's going on in class, and then you're doing bad on all the tests. That's how it happens when you wait for me to give you the answer all the time. Make sure you do these examples. Finish them by tomorrow. Also by tomorrow, memorize all the rules that I gave you. From now on, I will assume you know these things, and if you don't, it's going to lead to problems down the road, I promise you. So I will see you guys tomorrow, bright and early. We'll do these examples and then start some topics.